So once we go through factoring trinomials, then we'll get into one last voltage divider. This one we call our bipolar voltage divider. So we're going to use this to basically what you do is you set it up in such a way that you can get both positive and negative voltages coming off of one circuit. But before that, so factoring trinomials. So basically one of the things that we need to do is like I said, we're going to be breaking things apart to separate them into individual components that we can then take and divide out, subtract out as we go through to simplify answers down later on in our electronics career. So if I have a problem to start with, that is 2x squared plus 7x minus 15. So what I need to do is I need to factor this guy out into its individual terms. Now, there's a couple of tricks that we have to do this. There's no real way that I know off the top of my head on how to just flat out calculate it. You're going to have to do a little bit of trial and error as you go through these. And this is, like I said, this is the method that I go through to solve them. So the first thing you're looking at is you're trying to create two individual terms that are going to be multiplied together to return us back to this value. Sometimes they can't be factored down, but the majority of the ones we're going to be working on, we will be able to factor them down. So the first thing you need to look at is these two terms. What do I need to do to multiply together to get these guys? So especially with this, what are the factors that I can split this apart to get 2x squared into? Like, what's the factors of 2x squared? 2x and an x. So lucky for me, those are my only options that I can look at. The next part is I need to look at terms that the last term can be split into. And what do we have there? One and 15, 3 and 5, 5 and 3, 15 and 1. So all the different combinations that we could possibly have. And the reason we'll do this is this will get important when we start dealing with other values. One of the other ones we have to look at is this number positive or negative? So if it's a negative value, we know that one of these two has to be negative, because a positive and a negative multiplied together will give us a negative. Two negatives will give us a positive. So as we're considering this, we need to be able to find ways of getting this to where the terms that we get are going to be multiplied or added or subtracted together to get this middle term. So the other thing we also have to consider is we have this 2x. So one of the things we can look at is, so these are our factors, and we need to look at the sums. Okay? The other thing we have to consider is we also have a 2. So we have a 2 times this on this first step. So we have to basically use these values to come up, how am I going to get 7x out of these combinations? So right off the bat, we can kind of look and we're like, okay, well, if we have 2 plus or minus 15, 15 plus or minus 2, is that going to get us anywhere near it? No. When we know we're going to have, one of these is going to be negative, we just don't know which one. So one thing we could look at here is if we make all of these negative, that's going to cover which side our negative goes to. Right? Is everybody tracking with me? So the first thing that we have, so we have 2 minus a negative 15, or minus 15, that gives us negative 13, which is not what we're looking for. The next one, we've got 2 times 3, which is 6, minus 5, that gives us 1. We've got 2 times 5 minus 3. That gives us 7. And the last one, we have 2 times 15 is 30, minus 1 is 29. So even using trial and error, we can quickly calculate what do we need to get to, or what do we need to get us to this plus 7x, which is this grouping right here. So when we do that, we know we're going to have the 5 here, we're going to have the 3 here, and the 3 is negative. So now we can go through and we can just check. We've got 2x times x gives us 2x squared. 2x times negative 3 is minus 6x. I do have this backwards. Yeah, you're right. I flipped that. I apologize. I got ahead of myself. Let's back up. You got to make sure you're putting what you're multiplying together in the right place. So the 2 is going to be multiplied with this second value, not this first value, which is what I had it originally. So I apologize for leading you astray. So again, we'll go back through and we figure out these values. And it could be where we have to flip them again. So again, we look at our values. So yeah, like I said, so finishing up with this one, which was my first thought, we had 2x, that gives us minus 6x. The 5x is plus 5x. We do get our minus 15, but then this reduces down to, so obviously I did not do it right, and that's why we're doing the double check, because I explained it wrong. So again, we look at this. We end up with, so we have 1 minus 30, negative 29. We got our 3 minus 10. We got our 5 minus a 6. We get negative 1. And we got our 15 minus 2 is 13. So we've got our negative in the wrong spot is what it comes out to be. Yep, we just flip them. And we change the signs. Come on. So the negative 3 is going to attach to here. And we end up with it. Now if we go through and double check this value. Why aren't you erasing? We got our 2x squared plus 10x minus 3x minus 15. That's going to reduce down to 2x squared plus 7x minus 15. So once in a while, when you're doing this, you might have to go back through and check your negative. And in that case, all you do is just flip your sign to the other side. We knew that one of those had to be negative based on that. Make sense? Let's look at another one. They get more difficult when you have factors that look like this, because you have to take that into account, which I had flipped. So we've got x squared plus 7x plus 12. What are the factors of this first one that we have? X and x. Makes it easy. Okay? Then we got to look at the factors of 12 that's going to add together to give us our middle number. What would that be? 3 and 4. And since we have just the same term on both sides, it doesn't matter which one we put first. Does that make sense? Again, we could go through the same method. So our factors are 1 and 12, 2 and 6, 3 and 4, 4 and 6, or sorry, 4 and 3, 6 and 2, 12 and 1. And again, we're adding because this guy for is positive and this guy is positive. If this guy was negative, we would be subtracting, usually. So we end up, if we were to add these together, we would get 13, we would get 8, 7, 7, 8, and 13. Again, that's what we're after, and it does not matter which one we put first. Okay, let's work. Does that make sense? These are very basic. Some of the other ones we're going to run into are going to look like this. Why did that draw green? I clicked on that one. The technology hates me today. Now we've got two variables located in this, but we can factor it down. One of the things we would want to look for first, is there anything in here that I could factor out to make it easier? We could factor out a 2. Make things a little bit easier for us. We could also leave that guy in there for either way. Okay, so now we're going to be looking at factors here. So what do we have? What are we going to have on each of our factors? How do we get our a squared? We're going to have an a and an a, and we're going to have a b and a b. We have to, because we have a squareds and b squareds. So now we just have to figure out what are my factors of 6 that when I add together, that multiply together give me -6, but when I add them together, I'm going to get a positive 1. 3 and -2. Okay? So where do we put what? Does it matter? So we've got a 3 and a -2. And in this case, it does not matter because we've already taken that out of our equation. Also, what you might see is now that we have just this multiplication problem, we could take this 2 and distribute it back into this guy. So the answer we could see on there is either this one right? We haven't broken any rules. We're still distributing things around. So let's double check. Is that going to give us the same answer? So if we take 2a times a, that's going to give us 2a squared. We have 2a times a -2b. That gives us -4ab. I think we're going to run into a little bit of a problem. No? Oh, yeah, you're right. We have a plus 6ab. For some reason, I was thinking that I was adding them together instead of multiplying them. And then we get a minus 12b squared, which, when reduces down, those will cancel out and we'll be left with our 2ab. So, when you're looking at these guys, see if there's anything you could factor out from the beginning, make your life a little bit easier. You don't have to deal with such large numbers. And then break it apart. You have your first term, you have your second term. You can put those in their places. You also know if you have variables. You also know you take this guy, what factors of this have to add together to equal this when they multiply together to give me this value. Does that make sense? I wanted to make sure I covered those before I forgot them. So moving forward with the theory, so the one thing that you guys will be recognizing is the math that we cover in 1 week starts applying the next week. And I think it's next week or the week after we will be getting into learning and understanding the basics of logs. Let's see, where are those? Week 6. Week 6 we get into logs, natural logs, imaginary numbers, complex numbers, and then the week after that we get into capacitors, where all that will start to apply. Yep. And then your minds will just go explosion, and then I'll have to clean up brain matter all over the place. All right, so bipolar voltage dividers. Give me a second to draw this circuit out. If you cover up this half, what is it? It's what we did yesterday. Now we've just taken it and mirrored it on the bottom. You could. There could be. Not that we're going to do in class, but there could be. Well, this is like I said, this is what your boss or your customer is like. Hey, I need one circuit that'll power 4 devices, and they'll give you those 4 devices, and you're like, hey, I can do that. Here you go. All right, we have. Oh yes, I forgot one part. Forgot one little guy right there. All right. So we have our bipolar voltage divider. We have 4 resistors in series, which is what we have to solve for to get this guy to work. We have resistor 5. This is our shunt resistor. Think of it that way. Everything we're not using is going to get pushed onto him. We have our load resistor A, which is 24 volts, and it requires 10.55 milliamps. Our load B is 10 volts at 2.5 milliamps. Our load C is 10 volts and 2.455 milliamps. So I flipped those, sorry. So RLD is 10 volts, 2.455 milliamps, and RLC is 5 volts at 6 milliamps. This will be one of the ones that you guys will build and test in lab as well. Yes. Yeah, it'll be next week's. All right, so the first things that we have to do is, like I said, we're trying to figure out what are all the currents going to be, where are the currents going to go, what would I measure if I was to physically break this circuit apart as we go. We're going to use pretty much all the tricks and tools that you guys have at your disposal right now. We're going to use Kirchhoff's voltage and current laws. We're going to use Ohm's law. We're going to use our parallel branches. We're going to use series. Everything that we've used is going to help us solve this guy. All we have to do is just break it down into steps. So the first things that we can do is we can go through and solve what the voltage drops across all these resistors are. That way we have half of the pieces needed to solve for the resistors to build this guy. Okay? So starting with a voltage, where do we want to start as far as the voltage? Which one would be easiest to do? R5? Okay. And why and how? Explain your thought process. Okay, exactly. Because like you're saying, these two branches are in parallel. We have 24 volts here, 10 volts here. So that means from this point to this point has to drop 34 volts between all four of those resistors. And whatever's left has to be dropped across here. So that is 13 volts. One thing I'm going to do is I'm going to go through and I'm going to name these nodes. So as we're doing calculations, we can reference where on our graph we are, or where on our circuit we are. So this one's going to be labeled A. This guy is B. This guy is C. This one is D. This is E, F, and G. So these are our test points. Okay, so now that we have the 13 volts established across R5, what other voltages can we go for? R2 and R3. So what's the voltage of R2 and why? Because it's in parallel with load B. R3? 5 volts because it's in parallel with RLC. Now, let's see. I'm going to change colors. So the pink is what we're given, the green is what we're calculating. Okay, so now we have those. What's the other two voltages, R1 and R4? Yep. So that is 14 volts. So R1 is in parallel, or this whole branch here from A to C is in parallel with this branch here. So we have 24 volts across this whole thing. We're dropping 10 of it here. We have to drop the rest of the 24 there. Same thing with down here, just like the circuits we were doing yesterday. Across this full thing from here to here, we have volts. We're dropping 5 volts here because we know that guy. So we end up with how much voltage across R4? 5 volts. Okay, we've at least now established the voltage drops across all these guys. Now comes more of the hard part, is we have to figure out where are my currents going to go. What's one current? Yes? For R5? So from here to here, those guys are all in parallel, correct? We have 24 volts and 10 volts in parallel, so that gives us 34 volts in parallel with this guy. So across all four of those resistors, we have to have 34 volts, and we're supplying 47 volts. Okay. So this is where the series parallel part comes in. So we're dropping 34 volts from here to here. We need to get up to 47, so this has to drop to 13 volts. Yep, it takes everything else that we're not using. This is our shunt. It's going to be one of those. So the other, Yes. Basically, we're shoving everything we don't want onto this resistor. We're going to use that a lot, especially when we get into power supplies. We will have a portion where we want to split up AC and DC voltages to flatten out our line, and we'll use a shunt resistor. When you're building your power supplies, this is where your power resistor is going to have to come in. That resistor is going to be handling 5 to 25 watts, generally. Yep. Okay, so the other thing, like we said, with these types of circuits is we have bleeder current. So bleeder current is going to be where it is only current that is not used by any of the loads. The way to determine where the bleeder current is for one, we could just pick one and see if everything matches up. Or we have to look at whichever node. So think of this as one node of our voltage dividers. This is another node. Whichever one has the higher current, that's the one where the bleeder current is going to be found. So in this case, on our top node, we have 10.555 milliamps and 2.5 milliamps of load current. So that gives us, so I load A and B is 10.55 milliamps and 2.5 milliamps. So that gives us a total of 13.055 milliamps. And the reason we can separate this is because of this ground. If we don't have that ground there, this won't work. The bottom one, so I load C and D is equal to 2.455 milliamps and 6 milliamps. So that gives us 8.455 milliamps. So which one is larger? The top one. So our bleeder current is going to be 10% of the node that has the higher current flow. So which means bleeder current is right here. Yep. Do what? So the bleeder current, all it is, we're establishing how much current is not going to be used by our loads. In this class, we are assuming, and we're kind of generalizing it, that it's going to be 10% of our total load current. That's just our standard. No, the power is the heat. So power is heat. This is just the current flowing through this point. And the reason why it's so special is because if we have the 47 volts and we have a current meter here for our R2 and we read this value, that's all we have to do to verify that this entire circuit is operational. So that's why it's special, because it 2 measurements and we can verify this entire operation of this guy. Because if that bleeder current is changed, something is wrong. So it's just a special location that we can use to test these voltage divider type circuits. That's all it is. So with that, now we have the information we need to start solving this guy. Okay? We know current is flowing this direction. It's going to come here and it's going to split. We're going to have current going this direction. We know we're going to have current flowing this direction. And we know we're going to have current flowing this direction. Same with this. We'll have current flowing this direction. And we'll have current flowing this direction. And this guy. We know those are going to happen because that's the current paths. What we don't know is we have to find out currents flowing between these 2 nodes. And that's what we're going to determine is where is this current going. Okay, so when we come around, let's look at, I guess there's a couple of nodes we could start with. We could either start up here at R1, or we could start over here, or so yeah, basically at point B, point A, or we could start over here at point E. And the reason I say to know where we start is looking at all the connections. Where do we have the most information? Using Kirchhoff's current laws. We know the current going into this node. We know one of the currents going out of that node. How many other connections do we have? One. So we can figure out how much current is either going to be coming in or going out of that node to equal out. They have to be equal. Same with right here. We know how much current is coming up here through our bleed. We know how much current is coming up here through our load. Those will combine together to give us that current, and then we can start working that direction. So we have one of two places where we can start. So that's the other part of troubleshooting and understanding these circuits is, what information do I have? Okay? So where would you guys like to start? Over here at point E or over here at point B? E? Okay. So coming in here to point E. Slide this up a little bit. So at node E, we have 2.455 milliamps coming in. We have 10.555 milliamps leaving. So how do we have to make this balanced? Do we have to have more current coming in that node or more current leaving that node? We have to have more coming in. So at node E, we know we have 10.55 coming in. We know, or going out, we have this coming in. So to satisfy Kirchhoff's current law, these have to be equal. So we end up with 10.55 milliamps minus the 2.455 milliamps. How much? 8.1? So we have to have another 8.1 milliamps coming into that node to be able to supply the current going through our load A.
So is that going to break off the first current then, or?
Yes. So now that we have this value, I'll change colors again so we can add these in. We have to have this current coming in to node E, and it's 8.1 milli. If you actually got in here, and if you had a wire, you could replace that wire with your current meter, and you would measure 8.1 milliamps in that connection, in that direction. And remember, we're measuring from negative to positive. So if you put your meter to match that, you're going to get a positive value. If you flip it, it's going to give you a negative current. Okay. So now we have that node completed. Where can we go from here? So like I said, just looking. E, we're good as far as currents. D, we still have some work on. C, we don't know how much current's coming out there. F, we don't know. G, we don't know. And those other ones yet. Okay, we can move back to node C, or should we move back to D? So we started at E, let's go back one. Okay, so now we look at D, we know, so we have node D. I'll try and do this. We have 6 milliamps coming in from our load C. We have 8.1 milliamps going out, which is what we solved for before. What else do we have connected to it? 2.5 milliamps going out of that node. And the last one, the last connection, we don't know, which is what we're going to solve for. So let's put these together. So we want to combine the outs together and we want to combine our ins together. So we end up with 6 milliamps going in, and we have 10.6 milliamps going out. So again, using Kirchhoff's current law, we have to have the same currents going into a node as exiting a node. What do we have? Do we have more current coming in or more current going out that we have to account for? We have more current going out, so we have to have more current coming in. And how much do we have? And that is coming in to balance everything out. This is just like chemistry. We have to have balanced equations on either side. So, we look back up at our circuit. We have 4.6 milliamps coming into point D, so that means this current has to be going like this. Now we've solved for all the connections at point D. Yep, coming into point D. So again, we'll draw our arrow with the direction the current's flowing. So now we can look back at point C. So we're just going to kind of keep walking backwards, and then we'll circle around and get the other ones as we come around. So we're going to look at point C. The ground, we're not going to have any current flow because it's just there as a reference point. That's just where our voltmeter is going to go. So coming into point C, yep. So at point C, we have bleeder current leaving. We have this 4.6 milliamps leading. So we've got 4.6 milliamps going out. We have 1.3055 milliamps also going out. So to satisfy Kirchhoff, we have to have how much current going in? Everybody see that, where we're at so far? So now, we know that this is the current coming through. And again, we can see, again, this is not our bleeder current because we have the 5.905, but it also has some current that's going up through our load. So this value here still contains some of our load current. So that gives us node C. Everything coming in and out of C is complete. Now we can go either direction. We can either step to F or we can step to B. Okay, F. So node F, has 5.9055 milliamps leaving, and it has 6 milliamps leaving. So what do we need to balance this node? 11.9055 milliamps coming into it. Okay? We come here to point G. What do we have? How much? Okay. So that gives us how much for node G? Which is right here. Okay, we're going to pause here just for a second. There it is. The current going through this resistor is our total current because it is directly in series with our power supply. Okay? The other thing we want to check for is this value has to be at least these two guys, because that's supplying the main current for these, which it is. We've got the 2.455 and we have our 10. So we're good. Okay? We come back around. This current is going to translate up to here as well, because this is also mainline current.
So if we use just current of ROA and define the current of R1 then?
Yep. So we'll back it up one step though, because we don't know the current coming through this guy. We could find it just using that. The 14.3605, we have 10.55, so we have 10.555 coming in, 14.3 going out. So how much do we have to have and what direction? Okay, we have to have that much current coming out. Okay, the other way we could calculate that is we have 1.3055 milliamps going in, we have 2.5 going in, we add those together, we get our 3.8055 milliamps. So now we should have all of our currents now calculated for the circuit. Granted, yes, there was a lot of steps, there was, but was it anything too painful? It's just reasoning through it, stepping through it using Kirchhoff. If you use Kirchhoff, you will not fail because it has to be satisfied. We cannot create energy. We can't just magically lose energy. So now we have enough information. We have all the currents. We have the voltages. Now we can go through and we can calculate what values of resistors we need to make this circuit work. Okay? So R1, we have 14 volts and 3.8055 milliamps running through it. How much resistance do we have, or that is required at R1 to make this work? Okay, R2, 10 volts at 4.6 milliamps. For R2. Okay. R3, 5 volts at 5.905 milliamps. How did my notes get so off? 846.74. Okay. So in my notes, if you're looking at it, this value here on R2 is incorrect in my notes. Okay, R4, 5 volts at 11.9055 milliamps. $419 ohms. Almost 420. Okay. So in lab as well, you will have to calculate the values needed for your load A, B, C, and D. But that's the whole idea. So now once this thing is solved and you're presenting it after you built it, the values you need to check is make sure your input voltage is correct and check your bleeder current. And if those are correct, your circuit is working just like it's supposed to. If not, it's a very, very, very happy accident. Because let's be honest, there is way too much stuff going on here to accidentally get things in the right ratios. Like, honestly, statistically, the odds for getting it right based on the number of components is next to none. I think you have a better chance of winning the lottery. So that's why the bleeder current is so special. Because with that, 2 measurements, and you can tell immediately if your circuit's working the way it should. So what would happen if you didn't have this guy connected? Kirchhoff would be happy. It would just be these numbers wouldn't make sense. They would all change. Okay? So let's say, like when you're building this guy, this one was not on the same row as those connections. Okay? You were off one hole. What's going to happen with the current this right here? It's not going to go that way. It's going to come in this direction. Plus, the voltage drops across these guys are going to completely change. So, just with that one, and then all of a sudden this guy is going to be absolutely different. Probably going to be more. Because there's less resistance. So you're going to have more current. But like I said, the cool thing is we don't really care how these things are wired. We just know they require a voltage and a current. And we are supplying them that. Do what? Because those are a piece of wire. Your resistance, it should be 0 ohms. And you're not shorting anything out, you're just connecting things in different places. Yes?
So, I guess in a work environment, if you were like told that a circuit wasn't working, like, would you have like that much information about the circuit?
Yeah, a lot of times you'd be given this information. You probably would have resistor values, and then say they would just have a block saying, heat pump or fan, or going in with the ice cream machine like I was talking about yesterday. Here's your ice cream maker. Here's the pump to pump from your 55-gallon drum into the ice cream maker. This is your cooling fan on the pump, and this is your cash register. Yeah, because you got to make money somehow. We're not doing this for free. So, like I said, so these ones, it doesn't really matter what they are. They are just something. They are a unit that you're using to control with specific requirements. We are building the control circuits to give us those. And the reason that's important is, especially in your projects, you guys will have things that you're building that you're going to want different voltages for. You're going to want, sometimes you want a negative voltage. When you deal with op amps, you want a positive and a negative voltage. So, yeah, op amps are fun. They're basically what you guys see on the board around you and what we come into. These are amplifiers that you build with transistors. An op amp is the simple version of a transistor amplifier. Op amps are everywhere. Any kind of, I think even in the calculators, they have op amps. So it's based, like your screen brightness, I think it's controlled by an op amp. They are everywhere. One of the things that we had up at ON is we had a board that was not, or we had a chamber. So what it did is we put on this layer they called photoresist, and what it would do is if you expose it to UV light, it would form a hard shell over where it was exposed, and it would protect the material underneath of it. Either when you're adding a new layer on or you're etching material away. So a lot of times you'd cover things over with a blanket of metal, and then you'd put this layer of photoresist over the top, expose it, and then you'd have this hard crust that would protect the metal underneath. You'd send it to another tool, and it would go through and eat away the metal that wasn't protected. And so then what you have to do is then you have to go send it through and clear off that layer of photo stuff so you can do it again. And we had an op amp in there there was 3 gases that was controlling. That's all it was, that eat the material away. And one of them, and no matter what set point you gave it, slammed it full open every single time. So it was dumping way too much excess gas into this chamber to use. And we troubleshot it down to a single op amp was no longer working. It wasn't giving us a gradual increase based on the signal. Any little signal, yeah, it slams it open full bore. We popped that sucker out, put in a new one, and the thing worked great. We saved ourselves probably, what was it to repair those boards? About $2,500 for a 40-cent part by sending it out to have somebody else repair it and then having it shipped back to us. So right there, that was one, that where we came down to this basic troubleshooting. We went down and we're tracing the lines on the schematic like you were asking. All we had was certain test points were supposed to give us certain voltages, and they weren't. And then we had to kind of work backwards. Well, what's this connected to? Where is this connected to? How do we build it up from here? Does that make sense? There's, like I said, there's a lot of little steps running through these guys, but just remember, follow the current. What is my current doing at each of these individual nodes? And walk it through step by step. Do I have enough information to be able to solve for this node? Or do I have to jump back a space to get the information to continue? Unfortunately, that's part of what electronics is. There's no direct guide map to solve every single problem. You have to be able to use your brains. And that's what companies are paying for. The degree itself, and I'll be honest, the degree itself is the opening for the door. Once you're in there, like with my job up and on, I use maybe 5-10% of what I actually learned in college. Except for how do you troubleshoot? How do you work through a problem? Sixth semester, you're going to spend a lot of time doing that. You're going to be given a schematic and be told, solve. What is this doing? What is it supposed to be doing? What are we measuring? And that's a lot of what it is. And a lot of them are different systems for the for upstairs for all the equipment that they have up there. We were able to get schematics for spectrum analyzers, for the TV signals. Like I said, that was, for me, the coolest part was understanding how a TV signal works before digital. But yeah, it's thinking from point A to point B. The degree gets you in the door. Your brain keeps you with the job, basically, is the idea. We're training your brains to think and understand in a way that you're presented with this problem. How do I fix it? Make sense? Okay. We will go through another one of these. I'll have you guys work through it, and then we'll work on solving it together. But first, we'll go ahead and send you guys to break, and I will start getting a new one written up on the board.